Hello everyone, welcome to my channel. This is a channel for educational purposes, and we like to take a look at theories of everything and go deep into them and just try to get a sense of them, eventually put it all together. But today is our 315th video on Dewey B. Larson's reciprocal system of theory. And Mr. Larson came up with this theory back in the 20th century, worked it out over most of his life, and wrote a lot of books. Toward the end of his life, he died back in 1990. Some of his followers took up the mantle and have put out some other books and articles since then. But the theory is very obscure and not well known, and it threatens to fall by the wayside if we don't kind of raise our consciousness about it, recognize that it's a beautiful thing and that it can help guide us in really every subject. It is a system of theory, meaning that if you understand the system, you can apply it to any and every subject. The basic gist of the reciprocal system is that we live in a universe made entirely of motion. Most people, the ancient Greeks, believed that the universe was made out of matter, and then Einstein came along and said, well, it looks like matter, but it's really energy. But for Larson, both matter and energy are just two different varieties of motion. And motion, for Larson, is the relationship between space and time. Now, the basic elementary kind of motion that we know of is speed. The bicycle is moving at 15 miles per hour. Well, that's 15 miles of space in 1 hour of time. Space divided by time is motion. But, and so that is a relationship between space and time. So as far as speed goes, Larson's theory holds up. Now, we can plug in any kind of scientific quantity and determine its space-time kind of coordinates. Acceleration. I dropped the ball out the window and it fell at 9.8 meters per second squared. 9.8 meters of space in 1 second squared of time. That is space over time to the second power, acceleration. And we can do that with other quantities too, such as energy. It took me 2 hours to move that thing 25 feet. 2 hours of time in 25 feet of space. Time over space is energy. And so on. Matter is time to the third power over space to the third power. Force is time over space to the second power. Pressure is time over space to the fourth power. Density is time to the third power over space to the sixth power. Now, density, density is basically mass over volume. So mass is time to the third power over space to the third power. Volume is volume is space to the third power. So when you put it all together, you get time to the third power over space to the sixth power. This is a consistent system so that you can check your work by making sure that the units work out all right. For example, E equals mc squared. Energy, time over space, times equals mass, time to the third over space to the third, times the speed of light squared. That's speed, s over t, to the second power. It's s squared over t squared. Multiply it all out, it works out. So that's an important, simplification of the units. Now, there are some caveats, such as time and space are both have their coordinate aspects, meaning that they both have aspects that are three-dimensional, or I would say 3 or 4-dimensional, but we're talking about X, Y, Z coordinates in space and some analogous thing to that in time. And then space and time both have their clock aspects, meaning that they are progressing like a clock. It's what Larson calls a scalar motion. And this is a motion that has a magnitude, but it has no specific direction, like a clock. A clock is always getting later and later and later and later, but it's not getting later in a specific direction. And in space, you could think of it as dots on a balloon. You blow up the balloon, all the dots are moving away from each other. That's the progression of space. In no specific direction. They're all moving away from each other. Space is getting farther and farther and farther apart. That is the progression of space, or clock space. And this was also observed by the Hubble telescope, that all of the distant galaxies are moving away from each other. And then space and time also are both quantized, meaning that they come in in a minimum unit. There's a minimum unit of space and a minimum unit of time. If you don't have a full unit, then you don't have that thing at all. So if you don't have a full unit of space, you don't have space. And if you don't have space, then you have time, because the universe is composed entirely of motion, and motion is the relationship between space and time. So everything has to be either time or space or both. And so if you don't have space, you only have time. Larson refers to this as the time region. If you don't have time, then you only have space. And Larson refers to this as the space region. So the region of less than 1 unit of space is what Larson calls the time region. And the region of less than 1 unit of time is what Larson calls the space region. And between those is when you have exactly 1 unit of time in 1 unit of space. Exactly 1 unit of space in 1 unit of time. They're functionally equivalent, because 1 over 1 can be inverted and you still get 1 over 1. But that is what Larson calls unit speed, and we know it as the speed of light. The speed of light is 1 unit of space in 1 unit of time. And so in Larson's system, this speed of light is really like the background of the universe, or the state of rest, the ether or the origin, the reference point, the 0 point of the universe of motion is the speed of light outward in all directions. The progression of space and the progression of time. And this differs massively from the Einsteinian viewpoint, which is that the speed of light is the maximum speed of the universe. Larson contends that the speed of light is the midpoint of the universe, and half of the universe is moving faster than the speed of light. This is the half of the universe that Larson calls the cosmic sector. And this is the half of the universe that the legacy scientists don't know anything about. What they do know about is what Larson calls the material sector. This is the half of the universe that is moving slower than the speed of light. And this conforms to Einstein's dictum that the speed of light is the maximum speed of the universe. Now, when one crosses that boundary, that speed of light boundary, which is really only feasible in massive stellar and galactic explosions, physically. When that happens, then the rules invert. And in the material sector, you experience coordinate space, 3 dimensions of space, and clock time. But in the cosmic sector, you experience coordinate time and clock space. You invert the relations of space and time. That's the reciprocal aspect of the reciprocal system of theory. So that's kind of how you put it together. What we're looking at today is, I believe, the third installment here of, we're looking at Larson's paper that he wrote back in the early 80s that is called scalar motion. Again, the scalar motion is a motion that has a magnitude, but it has no specific direction, like dots on a balloon that is being expanded. And as Larson had said earlier in this paper, scalar motion is a motion that scientists have known about for a long time, but they have not recognized its significance. In Larson's system, it holds fundamental significance. And and in particular, what he calls a distributed scalar motion, which is what you would consider if you have those spots on the balloon and you blow up the balloon, but the balloon, in addition to actually expanding, the balloon is also rotating. When the balloon is rotating, those motions are distributed over that, circumference or arc that the balloon is rotating on. So that is what Larson calls a distributed scalar motion. And he determined that electricity, magnetism, and gravity are all kinds of distributed scalar motions. Electricity in 1 dimension, magnetism in 2 dimensions, and gravity in 3 dimensions. Okay, now we are, again, this is the 3rd episode of this. So if you want to go back to the beginning of this paper, you want to go back a couple episodes and start there. But we will take over here. The insistence on viewing gravitation as a transmission process also involves a wholesale disregard of the physical facts. That viewpoint likens gravitation to electromagnetic radiation, and we hear about gravitational waves in the same way we hear about electromagnetic waves. But the two processes are entirely different, and it is very difficult to understand why anyone should ever connect the two. Electromagnetic radiation is an energy transmission process. A photon leaves an emitting object with a certain amount of energy. The energy of the emitting object is decreased by that amount. So, when a photon leaves the sun, the energy of the sun is decreased by that amount of energy that photon had. And then when the photon says the photon travels through space and reaches an absorbing object, delivers the energy, and the amount of the absorbing object is increased by that amount. So, the photon gets to Earth and it gets absorbed by the Earth's energy increases by the amount of that photon. Electromagnetic process. It's an energy transmission process. The intervening space, the distance, has nothing to do with the process except in determining the time it takes for travel. The process is independent of the distance. So it doesn't matter whether the photon has to travel from the sun to the Earth or whether it has to travel from the sun to Pluto. As soon as it gets there, the body absorbs the photon and the energy is transmitted. Doesn't matter how far the photon has to go, it still has the same amount of energy in it once it gets there. So the process is independent of the distance. In contrast to that process, the gravitational process is totally dependent on the distance. All you have to do is look at the gravitational equation. It's based on an inverse square law. The distance apart squared is the amount of the force of the gravity. In contrast to that process, the gravitational process is totally dependent on the distance. If there is no change in the distance, that is, if the two apparently interacting objects don't change their separation, then there is no change in the energy at all. And even if an energy change does take place, as happens in the case of a falling object toward the Earth, the increase in the kinetic energy of the incoming falling object is not obtained at the expense of the Earth. It's derived from the potential energy, the energy of position of the falling object itself. Much of the same considerations apply to electricity and magnetism. There are a number of other direct consequences of the scalar motion existence that have an important bearing on various physical problems, and I intend to cover them. That is, all those that I have so far identified in this new book. But I don't want to take the time to talk about them here because I want to leave time for adequate consideration of another very important finding, which, like the existence of distributed scalar motion, is significant enough to justify classifying it as the equivalent of the results of a crucial experiment. And that's what Larson, he pointed out earlier here, that's what he's looking for. He's looking for crucial experiments that, where the reciprocal system will provide one answer and the legacy science system provides another answer. And so it's a crucial experiment that can help determine, which one of these theories is correct, if any. And Larson said that, well, we don't necessarily have to dream up a crucial experiment. We can look in the past and we can look at other experiments that have been done in the past and they might serve the same purpose. The second important finding is a result of a well-known experiment, but it has not previously been recognized because a recognition of distributed scalar motion was a prerequisite for recognition of the new fact. As a preliminary, before starting to talk about that particular subject, I want to say a few things about speed limits. The present scientific view is that nothing physical can move faster than the speed of light. That belief is based on Einstein's interpretation of certain experiments in which an electric force was applied to the acceleration of light objects, such as electrons. It was found in those experiments that the acceleration did not continue at the same rate as might be expected from Newton's second law of motion, but decreased at high speeds at a rate which indicated it would reach zero at the speed of light. That indicated, of course, that either the force must decrease at high speeds or the mass must increase at high speeds. There is no physical evidence of any kind to indicate which is the correct alternative. So Einstein had to make a guess, and he guessed in favor of the mass alternative, that at high speeds, mass increases to infinity to the point where, you can't accelerate it anymore. And so therefore, Einstein determined that nothing can move faster than the speed of light because, the efficiency of the process turned to zero at the speed of light. According to Einstein's theory, the mass increases at high speeds and becomes infinite at the speed of light. On this basis, it is, of course, impossible for any higher speed to exist. So far as present-day theory is concerned, it makes little difference which of these alternatives is correct, because there is obviously a limit on a one-dimensional basis in either case. Since present-day theory does not concede the existence of multidimensional motion, which he demonstrated in the first 2 episodes here, the existence of multidimensional motion. That's really multidimensional scalar motion. The existence of a one-dimensional limit is equivalent to the existence of a limit on speeds in total. But when we recognize the existence of multidimensional scalar motion, then it's equally evident that the limit on speed in one dimension can be reached in each of the 3 dimensions. Again, he pointed out that for scalar motion, one dimension of motion requires 3 dimensions of space. So you need a 3-dimensional spatial coordinate reference frame in order to express 1 dimension of scalar motion. But there are 3 dimensions of scalar motion. The other 2 dimensions cannot be represented in a reference system, or at least not one that we have dreamed up yet. That does not mean that it's possible to achieve a speed greater than light by electrical means, because, as I pointed out a little bit earlier, the electric force is one-dimensional. That accounts for the fact that the electrical force was unable to reach any higher speed. But it does not preclude acceleration to higher speed by means of some other process, such as, for instance, the release of large quantities of energy in violent explosions. This brings me down to the second important physical fact that I've been talking about, but I want to pause for a moment to emphasize the continuing factual nature of the development of thought. The reason I need to do that is that the conclusion I am now ready to pull out of the hat appears in the theory of the universe of motion as a postulate, and it has some far-reaching consequences. Those who realize that both the conclusion itself and the consequences are part of the theory of a universe of motion are likely to suspect that I may have smuggled some theoretical considerations into the development of thought at some point along the line. So I want to assure you that's not the case. We're sticking entirely to the facts. We know from observation that the electric charge occurs only in discrete units. We have, such as, Planck's constant, is what I'm thinking, is what he's talking about. I might be wrong about that. We have identified the electric charge as a distributed scalar motion. Now, there's no difference between this scalar motion and any other scalar motion so far as the motion itself is concerned. The difference is only in the nature of the coupling to the reference system. Once we have established that the electric charge, which is a scalar motion, is limited to discrete units, it then follows that scalar motion occurs only in discrete units. Those of you who are encountering that conclusion for the first time may not be very much impressed by it. In fact, with all the buildup I have given it, it may come as somewhat of an anticlimax. But those of you who are familiar with the theory of universal motion will realize the great significance of deriving this conclusion from purely factual premises. At one stroke, it raises a very substantial portion of the conclusions that have been reached with respect to a universe of motion from the status of theoretical conclusions to the status of established facts. The only property of scalar motion, of a scalar motion, is magnitude. Such a motion is a relationship between a space magnitude and a time magnitude. Now, we have further found that those are integral magnitudes, so that the properties of scalar motion are the properties of integral magnitudes, integers. It then follows that we can derive the physical properties of scalar motion under any particular circumstances by translating the mathematical properties of reciprocal integers, which we already know, into the appropriate physical language. This, of course, is a general principle of extremely wide application. In our ordinary view of motion, the minimum amount of motion is zero, and zero is therefore the condition of rest, the condition from which effective magnitudes are measured. In a reciprocal speed system, on the other hand, the minimum speed is unity, because anything less than unit speed is not speed. It's inverse speed. Similarly, the minimum inverse speed is unity. It follows that in such a system, unit speed is the condition of rest, the condition from which all speed magnitudes are measured. Expressing that in another way, we can say that unit speed is the natural reference system. The natural reference system for scalar motion is not a fixed system, it is a moving system. The motion of the time component is universally recognized. We all recognize that now is not something that stays put. It continually moves forward. The essence of the new finding is that here is an entity of the same kind. It likewise continually moves forward. What this means then is that all physical objects are continually being carried outward at unit speed relative to the fixed reference system. In most cases, that outward motion cannot be recognized, but where the gravitational effect is absent, as in the case of the photons of radiation, we can observe the outward motion. Photons move outward at the speed of light. The same is true where the gravitational effect is practically negligible, as in the most distant galaxies, which are likewise moving outward at almost the speed of light. Another important consequence of the reciprocal relation that we have now established is the symmetry around unit speed, which means that there is motion in time as well as motion in space. I think I'm going to stop right there. Even right, though we're in the middle of a paragraph, he's kind of getting into a new idea there. And we will take over at that point starting tomorrow. Now, this is important stuff, obviously, fundamental to the reciprocal system. I understand most of it. There's a few questions that I have. But just hang in there. If you don't understand everything, just put it in the back of your mind and let it and mull it over, and don't reject anything right out of hand. Just persevere. Just hang in there, and it takes a little while, because you have to unlearn things at the same time that you're learning new things, new and different concepts, and they overrule some cherished concepts that you may have. But as he says, the facts are the facts. And there certainly are plenty of facts out there in the history of science that don't make any sense. So he's attempting to correct some of those things. So I think he's worth listening to for that matter, for if no other reason. All right. Thanks for tuning in today. We will talk to you tomorrow.